Hello, Dr. Cole here. Let's get started on the next lecture. Okay, so what we're doing now is we are moving on to ANOVA, and this is the ANOVA folder that was shared with you. Let's start with the lecture. Okay, let's make it a little bit bigger. There we go. Okay, so this is part one. There's going to be two lectures on ANOVA. ANOVA is an inferential statistic. We learned that in the last lecture about inferential statistics. We started with the t-test. So ANOVA stands for analysis of variance. So if you think about the words here, we're looking at the variability in the scores, and we're using the statistics to analyze the variability, which is basically what happens with the t-test. The only difference is the t-test is just two means. So here we have a statistical technique used to determine if there are significant differences between the means of three or more groups. ANOVA is useful when you're comparing multiple groups to see if at least one group mean is different from the others. To perform an ANOVA, you must have a continuous response variable. So the dependent variable needs to be a continuous variable and at least one categorical factor independent variable with two or more levels. ANOVA is also part of the general linear model or GLM family of statistical tests. And some statistics software refer to ANOVA as GLM. For example, in SPSS, there's a group of statistics called GLM, and that's where you would start to set up your ANOVA. In JASP, it's called ANOVA. It's easy to find, and we'll be learning that. So here's a step-by-step breakdown of the concept. So why would we use ANOVA? Well, let's say when we're comparing two groups, a t-test could work fine. But when we have three or more groups, using multiple t-tests increases the chances of making a type 1 error, incorrectly rejecting the null hypotheses. And ANOVA solves this problem by testing all groups at once. So let's say you had three groups. You could do a t-test of group A versus B, then you could do a t-test of group A versus C, and then a t-test of group B versus C. And each time you do that, you're compounding the possibility that across all three groups, the null hypothesis should in fact be accepted. So that's where you're increasing the type 1 error. And ANOVA solves this by testing all the groups at once. So the basic idea of ANOVA divides the overall variation in the data into two types. The first type of variation is called between group variability. This looks at how much the group means differ from the overall, the grand mean. And then within group variability, this looks at how much individual observation differs within each group. ANOVA compares these two types of variability to assess whether the between group variability is significantly larger than what you'd expect by chance, given the within group variability. So when we think of the null and alternative hypothesis in ANOVA, the null hypothesis is that all group means are equal, right? There's no difference between the group means. If we find the p-value is less than 0.05, or whatever level of alpha we want to accept, right? If we wanted to set alpha at 0.1, meaning the 90% level of significance, then we would reject the null hypothesis if the p-value is less than 0.1. But let's, again, stick with industry standards, 95% level of significance, alpha equals 0.05. So if the p-value is less than 0.05 when we run the ANOVA, then we can reject the null hypothesis and we will infer the alternative hypothesis that at least one group mean is different from the others. And we will want to find out which group mean is the different one. And we'll get to that when we jump down here to number 8, when you do a post hoc test. But let's lead up to that. So when you conduct a t-test, we're using the t-distribution or the t-statistic. When we conduct ANOVA, since it's a little more complicated because we're looking at multiple groups greater than 2, we're using an F statistic. So the result of an ANOVA test is the F statistic, which compares the variance between the group means to the variance within the groups. A large F statistic suggests that the group means are not equal. If this F statistic is greater than a particular critical value based on the sample size, based on the p-value, then we will reject the null hypothesis and conclude or infer that at least one group mean is different at that particular level of significance. The types of ANOVA. There are different types of ANOVA depending on the experimental design. And for this course, we're going to be learning about 4 types. 4 types of ANOVA. The one-way ANOVA compares means of 3 or more groups based on one factor. The two-way ANOVA compares means across groups based on 2 factors. And we can also look at the interaction between those factors. And that's what we're going to cover in this lecture. And then in the ANOVA Part 2 lecture for next week, we're going to look at repeated measures ANOVA, which is when we have the same subjects measured multiple times. For example, pre-post tests, or if we're doing a drug study and we have the same animals tested at different times with different doses of a drug. And also next week, we'll learn about the mixed design ANOVA, also called a between within ANOVA or split plot ANOVA, when our experimental design includes both between subject factors, like variables where different participants are assigned to different groups or conditions, and within subjects factors, which is where we have repeated measures, variables where the same participants are measured multiple times under different conditions or at different time points. This combination of between subjects and within subjects factors makes the mixed design and ANOVA particularly useful for studies where you are interested in both group differences and changes over time or conditions within the same participants. Again, that's next week. So this week, this lecture, we're going to do one-way and two-way ANOVA. And these are called the between subjects design because they involve comparing differences in a dependent variable between groups of different participants, where each participant is assigned to only one group or combination of conditions. In these designs, each group consists of different individuals and comparisons are made across groups rather than within the same individuals. So next week, when we learn about within subjects or repeated measures design, the same participants are tested under all levels of the independent variable. For example, if you were testing different teaching methods in a within subject design, each participant would experience all 3 methods, and their test scores would be recorded under each method. In this case, the comparisons are made within the same subjects, as the same individuals are measured multiple times under different conditions. Again, the distinction between subjects and within subjects or repeated measures designs is based on how the participants are grouped and how data is collected. We're doing between subjects designs this week. So different subjects in one group compared with different subjects in another group. So we're looking at the variance between the subjects because they're assigned to different conditions or different levels. And this will make sense in a moment when we get into the data and see how the data are organized. Some assumptions it's important to understand, like before, since it's this parametric inferential statistics, we're assuming the data are approximately normally distributed. We're also assuming homogeneity of variances, also called homoscedasticity, that the variances in each group are similar, and that the observations are independent of each other. If the observations are not independent of each other, then we're violating a key assumption. we want to look at the effect size. So even though we might find a p-value less than 0.05, the actual effect may be very small, and then we would just want to be sure that we're reporting that while we found statistical significance, it's not a particularly strong effect size. So when we did t-test, the effect size statistic was Cohen's d. Here, when we do effect size, the statistic is called eta squared, or this symbol, Greek letter eta squared. Eta squared is a measure of effect size that indicates the proportion of the total variance in the data that is attributable to the factors in our ANOVA model. So in a few weeks, when we get to regression, you'll see we'll be looking at R squared as the effect size statistic in regression analysis. And so for ANOVA, eta squared can be interpreted like R squared. The guidelines for interpreting are similar to Cohen's. When we have an eta 0.01, that's small. Eta around squared around 0.06 is medium. And eta 0.14 or larger is larger. So if we were to have found an eta 0.14, we would say about 14% of the variance in the dependent variable can be explained by the differences between the groups, which is considered a large effect. Now, if we find p-value is less than 0.05, we're going to visualize it, so we will see the plot and we'll be able to see where the difference is, but it's also important to run a follow-up statistic called a post-hoc test to actually see which group is different from another group. And one of the most common, there's different types of post-hoc tests that you'll see when you get into JASP, but one of the most common is called Tukey, and it's actually referred to as Tukey's HSD post-hoc test, which is used after you conducted an ANOVA and found a significant result. It helps determine which specific groups are significantly different from each other. Why will we use a post-hoc test like Tukey's HSD? But when we conduct an ANOVA, it tells us whether at least one group is different from the others, but it doesn't tell you. So let me rephrase that. When we conduct an ANOVA, the p-value is going to tell us that at least one group is different from the others, but it's not going to tell us which groups are different. The post-hoc tests, like a Tukey's HSD, are designed to make pairwise comparisons between group means to identify where these differences occur. So it's as if we were going to then go back and do a bunch of t-tests, group A versus group B, group A versus group C, group B versus group C, but it does some corrections to adjust for the fact that multiple comparisons are being made, and there's this phenomenon called the family-wise error rate. So the chance of making a type 1 error increases as you keep making multiple tests, and so Tukey's controls for that. So what does it do? It's doing pairwise comparisons. It's comparing the means of all possible pair groups. It's adjusting for these multiple comparisons. It's controlling the type 1 error rate. And it's making some assumptions, assuming equal variances, and we're going to use it after we do the ANOVA, and we'll see those results and learn from it. Okay, so let's get started. Let's first start with a few examples of practicing a one-way ANOVA. So what does one-way mean? One-way means we have one independent variable. That independent variable needs to be a categorical variable, or what we learned in R is referred to as a factor variable. It needs to have, well, technically needs to have 2 or more group levels. If it only had 2 group levels, we could just use a t-test. So we're using ANOVA because we're assuming that or we have data where we have 3 or more levels and we have one dependent continuous variable. Now, we're not saying, I mean, you could use an ANOVA if you had a independent variable that had like 10 levels. Like if you took a continuous variable and broke it up into 10% intervals. But in that case, if we're starting to get so many different granular levels, it becomes very difficult to interpret because it's if you have 10 different groups, and then your post hoc comparison is going to be really complicated looking at all of the different group comparisons. So ANOVA is quite effective when, let's say, you have 3 groups, like a low, medium, and high, or let's say we have 4 or 5 different locations. Maybe we're comparing prices of real estate in 5 different cities, and we wanted to see, is one city, are the prices in those 5 cities different from each other, and then we'd find out which ones are different. And in our examples for this lecture, we're going to be doing very simple two levels and 3 levels and 4 levels. So we're not getting that complicated. Okay. And if the independent variable, right, on the x-axis, if that independent variable is actually a continuous variable, and you want to keep it as a continuous variable, and look at how the dependent variable changes as a function of all of the individual scores, that's when we use regression, and we're going to use that in a few weeks. We're going to practice in this lecture to take a continuous variable and turn it into a categorical variable. Remember, we did that last week when we did a median split, or we did the mean split, low, high, or if it's age, young, old. So that's when it would be appropriate to do an ANOVA, if we took a continuous independent variable and transformed it into a categorical or a factor variable. And if we just wanted to do a simple one-way ANOVA where the independent variable was transformed into a categorical variable with just 2 levels, we could use a t-test. But if we want 3 or more levels, like let's say we'd take an age and we turn it into young, middle-aged, older adult, we can't do that very easily with a t-test, so we would use ANOVA. And also ANOVA will allow us to do more complicated things, like look at 2 or more different categorical variables and see how the dependent variable is tested across that's called a 2-way ANOVA. So in this lecture, we're going to do the 1-way ANOVA, and then you'll see down here, we're going to give some examples of doing the 2-way ANOVA. All right, so let's start with the 1-way ANOVA, and let's start with the depression data. Okay, so let me describe it, and then we'll open it up in Google Sheets, and then we'll practice. All right, so this is the only data we're going to use this week. This is data from 294 adults, age 18 to 29. Actually, I think they're older than that. We'll look at the age. I think it's 89. I think it's a typo. 18 to 89 years of age, demographic characteristics, and self-reported depression. Here's the code book, so we can see what the data are. So we can see we have an ID variable. We have a variable that's going to tell us whether they're male or female. We have the continuous age variable, and like I said, I believe it's 18 to 89. And then we have a variable, we have a bunch of factor variables, right? So sex is already a factor variable, marital status is already a factor, education is already a factor, income is a continuous variable, we have religion, and then we have a series of items 1 through 20 that are self-reported levels of depression. And it's not important to understand what each question is. What we're going to do is we're going to take these 20 and use Google Sheets to create our summary score, right? So we will create the depression score that will be continuous variable. That's the sum of these. And then we'll learn in how to do Google Sheets to create another variable, an if then, but we'll use Google Sheets, and we'll use this later when we actually do regression. And then we have variables on whether they drink, their general health, if they see a regular doctor, have they been prescribed medication, have they spent time in bed, do they have acute illness or chronic illness? All right, so that's the data sheet or the code book. Let's go ahead and grab the data. Well, let's look at what our first experimental question is. So first thing we want to do is look at what is the relationship between employment status and depression, right? So we have here, we're going to be looking at employment as an independent variable. And then do we see differences then after we create this depression score, do we see differences in the mean depression anywhere in these different groups? One group being however many people reported there being full-time, however many people reported part-time, etc. Right? So that's our first question. So our null hypothesis would be that the mean depression is equal across all of the employment status. There's no difference. And if we find the p-value is less than 0.05, we can reject the null hypothesis, infer the alternative hypothesis. At least one group mean is different than the others, right? So let's open up the data in Google Sheets. Let's create a depression score first. So go to our folder. We've got our depression data. Let's download it so that we can open it up in our own Google Drive, a different Google Drive, and so we can access Google Sheets. So here I have Google Drive. Let me open up a Google Sheet. Okay. And then let's import the data. Upload it, browse. Here's the depression. Import the data. Okay, so here's what we saw in the code book. And yeah, clearly we see age is a larger value. We can look at the descriptive statistics in JASP in a minute. Okay, so let's go ahead and practice. Let me make this a little smaller. Let's go ahead and work in Google Sheets and do some more work. So the first thing we need to do is take these 20, right, C1 through C20, take these 20 items that were on a survey where each item was about whether you had depression. And if we remind ourselves of the code book, right, these items were scored rarely, sometimes, occasionally, most. So if we're going to create a sum, we've got to turn these words, right? We have to turn these words into numbers because you can't create an average of words. We have to turn them into numbers. Well, let me show you how to do that. It's really easy in Google Sheets, and let's just remind ourselves. So rarely will be a 0, sometimes a 1, occasionally a 2, and mostly a 3. Okay, so what we're going to do is we're going to go ahead and highlight the columns that we want to replace the words with numbers. So then we go to edit, find, and replace. And actually let me back up. Probably the easiest way that I like to do it is to first grab the word exactly as it is, because that way you don't have to make a mistake typing it. So let's just copy rarely. We're going to click right here. So actually the whole data set is highlighted the reason we can do that is because we look at the code book, we don't see anything that has also the words rarely, sometimes, occasionally, mostly. If we did, we would just want to make sure we're just highlighting the specific columns that we want to be finding and replacing. So we have in memory this word rarely. Now we can go to edit, find and replace. So we're going to do the Control V. We're copying the word rarely. We're going to replace rarely with what? What was our code book again? Rarely needs to be a 0. Okay, rarely is a 0. So we're going to do 0 and we're going to say replace all. So it replaced all of the rarelies with 0, right? So let's pick another one. Mostly. Copy, highlight the data again. What was mostly? Mostly is a 3. Okay. So edit, find and replace. Mostly becomes a 3. Replace all. Done. Occasionally, copy. Boom. What was occasionally? Occasionally is the 2. So edit, find, replace. Occasionally 2. Replace all. And then finally, sometimes is the 1, right? Okay. Highlight all the data, edit, find and replace. Sometimes is the 1, replace all. So see, now we've done an easy way of taking those words. We've taken a categorical qualitative variable and turned it into a quantitative variable. And it's actually a continuous variable that goes from the values 0 to 3. So now we can easily create a new variable. Let's put it here, insert one column to the left, and this can be our depression score, right? And so let's just simply do equals sum, because we can do sum, is because then we can get some cutoffs if we want to turn that sum into a categorical variable where you're depressed or not depressed based on some summary score. And so what is the sum going to be? So what I did again is I clicked here, I typed equal, and then I'm typing in the beginning of the formula and I see sum is there. I click on sum. So it already gives me the left parentheses, and now it wants me to put in all the values. Well, the values that we're summing together are C1 all the way through C20. And then we need to close the equation with the right parenthesis and hit enter. And now look what it does. It's saying, oh, okay, I get it. Should I do it for all the way down? And we can do yes, click here, or we can do control enter. So then it did it all the way down. So now we have the summary score has gone all the way down. And even though there's a formula here, when we bring this into JASP, it will bring in as the value. If you wanted to delete the formula, and I'll show you as an example, we could insert another column. You could take this and do copy, and then here when you paste, you do paste special, and you just do values only, and see it got rid of the formula. Sometimes it's helpful to get rid of the formula, particularly if you don't ever need the formula again and if you're going to start doing other manipulations. But for now, now that we just did that, and maybe you practiced along with me, why don't we do one more variable? We can call this one, we can call this this is the sum, and then this can be why don't we just do this as depression, and let's do an if then. And if you go back to our code book, you can see they already, when they did their research, they said if you're greater than or equal to a 16, you're depressed. So let's practice doing that in Excel. So now that would be equals, now we have a new formula, the if. Now in JASP, we did the if else. In Google or in Excel, if is basically if else. So if we have some logical expression is a value, then something happens. So we're basically saying if this score is greater than or equal to 16, then why don't we put in the word, so we'll use a quote, depressed, else put in the word normal, and then close it, right? So there we go. Now, since we already had numbers here, it didn't fill all the way down, so let's copy that formula and let's bring it all the way to the bottom of the sheet so that the formula is pasted in. And so now it did that if else, but we used Excel. So that was one of the things that I wanted to practice with you. So that's done. And I think that's all that I suggested that you do in practicing in Google Sheets. Yep. All right. So now we can take this Google Sheet. Let's go ahead and name it. Why don't we call it depression? And maybe we'll call it JASP. And then now we can download this CSV so that we can import it into JASP. Okay, so let's go ahead and start working in JASP, which is the next step. So now let's bring it into JASP. So let's go ahead and open up JASP. There's JASP. Okay, and then let's go ahead and import that data. Open, computer, downloads. There's the depression data. And here we go, right? So everything came in and we have our new depression summary score. We created this new variable that we'll actually probably work with in another lecture, but at least we just practiced that. And if we wanted to double check that I made that mistake on age, we could go to descriptive statistics. Let's just look at age for a second. Yeah, so age went from 18 to 89, so that was a typo. All right, so now we're ready to, let's follow along now with the lecture. Okay, I want you to practice a little bit of some recoding right in JASP. So let's take a look at our question again was employment status and depression. So we have our depression dependent variable. Let's take a look at the independent variable, which is employment status. So we've got 7 levels, right? Or 7 it's a factor variable with 7 levels or 7 categories. Let's see, do we have a lot of people? We had 249 people. We with 294 people. Let's see how many do we have in each of these categories. If we don't really have a lot of people in each category, maybe it's best to collapse some of these categories. Like if somebody is in their house, maybe they're quote unquote a house person, that probably means they're unemployed. So maybe it's best if we recode them as unemployed. Well, now we've already then gone from 7 to 6. And let's take a look at how many people are in school, how many are other. If there's not very many people here, maybe we'll just filter those out. We don't really know what other is, so we can't just assume it can go in any other category. So let's start by doing a frequency analysis, which I didn't teach you yet. So descriptive statistics. Let's look at the employee. And since it's a categorical or nominal variable, there's no mean, right? Because it's words. But we can come down here and do the frequency analysis under tables, and we can take a look at what we have here. So We have 38 people that are retired, 167 full-time, 14 are unemployed, 27 are house people, 42 part-time, 4 are other, 2 in school. Okay, so not very many other, not many in school. Quite a lot who are house persons. To me, that means unemployed. So let's recode house person as unemployed. And then when we do the analysis, let's filter out the in school and the other, which is another way of saying making them missing. Well, when you do statistics, it's going to delete those rows anyways if there's missing, so we can just filter them out. So we'll go back to our data and let's click on the employee, double click on it. So now we can see here, here's all the values. So to recode, it's very simple in JASP. Let's take house person and recode it exactly as the word for unemployed. And now it did it. It got rid of all of the house persons and it made them unemployed. And as we said, let's also filter out. So we're going to click here. That's going to filter out the others, and let's filter out the in schools. So now when the analysis is conducted, those are essentially missing, and there's no reason to look at the depression score for them anyways, because we're excluding them. So now we're good to go. And we practice that. And then now the next step is we can run the ANOVA on employment status as a predictor of depression. And then I'll show you how to do all of the pieces for that in JASP. All right, so now we go to, we can go back to look at the descriptive statistics. We can see now we just have the 4 levels, and now it's 288 people. And yeah, there's a lot of full-time people, but at least we have more than 30 in any one category, which is pretty good for when you're doing analyses between groups. So now we're going to go to the ANOVA, and what we're doing is this week is the one-way and the two-way are in ANOVA, and then next week we'll be doing the repeated measures. So let's click on ANOVA. So the one-way ANOVA is because we have our depression score, our continuous variable is our dependent variable, and then we're having one categorical, one factor, which is employee. So the ANOVA is automatically conducted. We can see the p-value is less than 0.05. So we have statistical significance. Let's go ahead and get that eta squared. So we can see the effect size. It's around 0.06. So it's like a medium effect size. And let's go to the post hoc test so we can see which groups are different. So we need to put the factor that we want to do the post hoc on here, and the default is Tukey. It's doing the Tukey's correction. And then the other thing we want to add is flag significant comparisons and give us a letter-based grouping table. So we can see here where we have significant differences, and those line up with the letters. So for example, retired is significantly different than unemployed, and we see retired and unemployed do not share the same letters. We also see full-time is significantly different than unemployed, and we see full-time and unemployed do not share the same letters. But everything else is not significant, and they share the same letters. Now we can do our descriptive plots. And so the x-axis will be employee. There we go. And I always like to have an error bar, and let's do the standard error. I like doing the standard error rather than the confidence interval. And it looks like the y-axis is correct. We could tweak that if we want. Let's bring this over here. It's not easy to see the x-axis, so we can just widen it out a little bit. Now we see all the words on the x-axis, and I believe we can change the name. Yep. So the x-axis can be called maybe employment status. And the y-axis, instead of depression sum, we can just maybe call it depression score. Okay. So then the next thing is just to write up our interpretation. So maybe over here, let's go ahead and add a note. Okay. Results of ANOVA found a significant effect of employment status on, or how about this? A significant difference in depression scores across employment status. Then how do we write that up? We would do F. Now we have 2 degrees of freedom. The first one is the between groups difference, which is the number of groups minus 1. What do we mean by groups? So we have 4 groups, 4 employment status groups. So that's why the degrees of freedom is 3, comma. And then this is called the within, or the residuals amount of degrees of freedom. And that's based on the sample size. So that's 284. We close that parentheses, we do equals, and then we report the F value, 6.15, comma, the P is less than 0.001, right? 0.001, that's the P, because our P is actually 0.005, so that's less than 0, so it's 99.9% level of significance, comma, if we want, we can do, can we do that symbol? I don't know exactly if we can put in the Greek letter eta. So you can, it might be here. If you can find it, that's fine. Maybe you can do HTML if you're so inclined. You can just do eta squared equals 0.06. Okay. And maybe put in parentheses in medium effect. And then we want to report the post hoc results of post hoc tests found retired, found that we've got the retired and the full-time are different than the unemployed. Tukey's HSD post hoc test found unemployed. Let's see, how about individuals who are unemployed have significantly greater depression than those who are retired or full-time. That kind of makes sense, right? If you're retired, you're enjoying life. You've already worked. You probably don't have that much depression. Now, the reason why unemployed and part-time are not different is because there's an overlap here, and there's also overlap with retired, full-time, and part-time. So we could probably say, no, that's all that we can say, right? Period. Okay. So I think that's it. And then you remember, you just do the, is it up here? Export results. This is your one way. ANOVA depression. And then that's what you'll upload into Canvas. Let's double check. That's looking good. Looks great. Pretty cool. Okay, let's move on. Let's practice another one. All right, what should we do next? Another scenario. All right, what is the relationship? Oh, again, a typo, I apologize. What is the relationship between income and depression? Well, as you recall from our data, right, if we look at our data, we're done with this, so we can close the employment status. And actually, let's go back and let's unfilter so that those rows are now available for another variable, another analysis. Okay. Income is a continuous variable. If we were to actually do an ANOVA with income, it would just be an absolute mess. Let's practice it for a second. So let's get rid of employee. Let's do another one. Actually, because we're going to want to clean this up. So let's put in income and see what happens. Now, it's got too many. It's not a factor variable. It's a continuous variable right now. So in fact, if we were to turn it, let's see if that works. Income, if we turned it into a nominal variable, will that do I think then it will do the ANOVA, but it'll just be crazy. Let's see. No, it's not the right kind of variable. It's not really a factor variable. It's still a continuous variable. All right, so back to it being a continuous variable. So if we wanted to do an analysis on income, we need to turn this into a factor variable. Well, and why don't we do it? Let's make 4 levels. So let's split it by let's make 4 equal groups. So how do we do that? So what we first need to do is understand what those split points are. So let's go back to our descriptive statistics. Let's put in income, and we don't need the frequency table anymore. And let's go ahead and click on statistics and say, make 4 equal groups. Okay. Now, from the coding book, we are reminded that income is thousands of dollars per year. And this must be a data set from like the 70s or 80s or something. So we can see here, if you make less than $9,000, right, you'd be in group 1. If you make $9,000 to $15,000, you'd be in group 2. If you are in the $15,000 to $28,000, you're in group 3. And if you're greater than $28,000, you're group 4. So let's go ahead and create a new variable. So let's click here and do insert column before. And let's click on the column, and then let's go ahead and create this new, why don't we call it the income 4 group, because we're going to make 4 groups. And it's going to be a nominal variable. And let's do our R code. And I've actually already given you the R code so you can use it to practice. So just grab this whole code, and you can see this is now a nested if else. Let's copy that, come back to JASP, paste the R code in here. And so what is it doing? Well, if income, right, it's looking at this, if this is less than or equal to 9, put in the words less than 9,000. If it's not, Now it's going to ask another if else. If income is less than 15, put in the words 9 to 15,000. Else, do another if else test. If income is less than 28, do 15 to 28. And if it's none of those three, then put in the 28. So click on converting types, and now we just transformed. We created a new variable. In fact, we can come back to descriptive, and let's split our income by the income that we just made. And we can see they're pretty close to being approximately the same size. I'm happy with that. And we can then see, right, that's the sample size for each one, and we can see how income was split across. So now we have this categorical variable, and we can go ahead and answer the research question in our ANOVA. What is the relationship between depression and income? So we'll use the categorical variable income. And now we have our new, we see it's also significant. We've got to go back and do our post hoax again and find out where it's different. We've got to do our descriptive plot again because we changed the variable. So there we have income, and there we go. Okay, let's widen it out a little bit so we can see better the x-axis. There we go. And what are we seeing? It's the difference is just that, right? The 28,000 is different than the 9 and the 15, right? There's not enough data, or it's pretty interesting that there's no difference really that was found between the 28 and the 9, but we certainly see visually the more money you make, the less depressed you are. So we would just do basically the same sort of pattern we did before. Now we have 3 is 290 degrees of freedom, 290. F is 3.56. 3.56. P is, we can do here, it probably makes sense just to report the actual P value. It's less than 0.05, so you can do 0.0146. Eta squared 0.04, which is again about a median effect. Results found: individuals who earn greater than $25,000 have significantly lower depression than those who, here, we can just basically summarize, who earn less. That's fine. It's not so much, we don't really need to get into the granular of why really was 28 not found to be significantly different than 9. It's almost, right? It's P.06. So it's basically, it's certainly significant at the 90% level of significance that those individuals who earn greater than 28,000 have less depression than those who earn less than 9,000. So that's why I made the decision as the statistician to just say significantly lower depression than those who earn less, right? That's a rule I'd like you to remember. You as the statistician, you use the statistics. Statistics don't use you. So in this case, we're making a decision as a statistician that because the p-value between the 9,000 and the 28,000 was 0.06, which is basically significant at the 90% level of significance. That's sufficient for our statement that significantly lower depression those who earn less. If we wanted, we could really be precise. We can say at the 90% level of significance in parentheses. Now, why again is it the 90% level of significance? Well, because the p-value here, it's greater than 0.05, and right, 0.05 is the 95% level of significance, but it's less than 0.1, and 0.1 is the 90% level of significance. So that's why making the statement at the 90% is really telling the truth. We're telling the truth that individuals who earn less than 20, yep, that should be greater. Individuals who earn greater than $28,000 have significantly lower depression than those who earn less than $28,000. Okay, I think that is right on the money. Good to go. And then, of course, export that as an HTML and you'd be good. So let's now practice the two-way. So what is the two-way ANOVA? So it's an extension of the one-way, but now we're just going to add in another factor, right? So now we have two or more independent variables. In this case, we're specifically saying two-way. You could have a three-way, which is three. We're keeping it simple. It's especially useful when you want to see not only the individual effects of each factor, that's called the main effects, but also how the two factors might interact. That's called the interaction effect to influence the dependent variable. So here's our question. What is the effect of gender and income on depression? So we already have our income variable. Let's now add in gender and let's take a look at what happens. So we have here our analysis. We have the income. Let's go ahead and add in gender or sex, right? Because sex is the gender variable. Well, what happens now? Well, now the ANOVA, right? But let's go ahead and finish it. So we've got the good, our eta squared is right. Post hoc, let's add in the sex and let's add in the incomes times sex. And then for the descriptive statistic, the plots, let's make sure we have separate lines. We can decide how we want it. I think it makes sense to, again, have the x-axis be the one independent variable, our income, and let's have the second independent variable, or the second factor, be the gender. So now we'll have two different lines. Okay, so now that we have all of that, and let's widen it out just so it prints better. Let's go ahead and look at the results of the ANOVA. So what do we see? We see income, excuse me. We see income has that p-value less than 0.05. So we have a main effect for income. Income does predict depression. Just like before, we see the more money you make, the less depression you have. But we see that sex is greater than 0.05, so we do not have a main effect of sex or gender. And then the interaction, the income times sex, which is why we get a visualization of two lines, is also not significant. So we do not have an interaction. And in fact, then if we look at the post hoc, we see, right, the main effect. We look at the post hoc, which is the main effect for income, which we had before. And now that we added a little more variability, a little more degrees of freedom, we can see that 9,000, now it's not even significant difference between 28 and 9 at the 90% level of significance, which in and of itself can be a very interesting discussion that sometimes if you don't make a lot of money, you're looking at other things in your life to help you not be depressed. Maybe money is not the most important thing. Maybe when you're in that medium range, like, God, I wish I made more money, so you're more depressed. I don't know. There's a lot we can interpret about that. Let's not get into that. But we also see here then the post hoc for female. Male is not significant, which is supporting already the same p-value that we had here because it was just two groups anyways. So that is going to be the same p-value. And then here where you really get the granular differences between male and female, and nothing emerges because there was no significant interaction. So looking at the post hoc of all of the different relationships between the different levels of income across males and females, the depression scores across the different levels of income and male and female, since there already was not a significant main effect, we're not going to see anything in the post hoc here. So in fact, we could go back just to make our output be a little less busy. We can get rid of that from our post hoc. And we could actually get rid of sex as well because sex was not significant. And then it's basically just what we have here. We reported out results of ANOVA. So now it's a two-way ANOVA if you wanted to. And in fact, it's something that's important. Or what some people do is they describe when you do a two-way in terms of how many different levels. So in this case, the sex has two levels, male, female, and the income has four levels. So what some people would say, it's kind of common, you would say a 2x4, right? Factorial ANOVA. Or if you want, you could say between subjects, right? Because this week is about all of the between subjects designs. Next week, we'll do the within subjects design or the repeated measures. So results of a 2x4 between subjects ANOVA found a significant difference in depression scores across employment status. So now we would report that F3 at 286 equals 3.0. We could do 3.09. P equals 0.0275. Eta squared is 0.03. In fact, since this was the independent variables alone are called main effects, and the independent variables multiplied times the other is called the interaction. So we could say found a significant main effect for employment status. Do a semicolon. A non-significant main effect for or of, I think of is the right word, main effect of employment status, main effect of sex. And you would report that, right? F1, 286 equals 3.24. P equals 0.07. There's really no reason to report eta squared because it's not significant, comma, and a or I use the semicolon, and a non-significant interaction effect of employment. Or we could put a non-significant employment times sex interaction effect. Okay. Boom. F, comma, now we have our interaction is down here. Again, 3, 286. You can put a space or not. I've seen it both ways. Equals 0.145. P equals 0.93. Okay, so done with that. Great. And one more example for teaching, or a couple more, I guess. What is the effect of being a regular drinker and employment status on depression. So, hold on, let me see. What did I do wrong here? Let me pause the video just for 1 second because I do see a typo. I don't want to confuse you guys. All right, apologize for that. Let's go ahead and do the effect of acute illness and income on depression. Okay, acute illness and income. So another 2x4. Let's practice that. Okay, so back to our ANOVA. So instead of sex, we'll double click to take that out. Let's put acute illness down here, acute illness. Okay, and oh, that's right. Yeah, I wanted to show this one because here we have a situation where we do have a significant interaction. So let's go ahead and plot that so we can see what that looks like. And let's look at the post hoc for that. We got to bring in there. We might as well just bring it all. Acute illness and the interaction terms. So we're getting post hoc for all of those. And then our descriptive plots. We have income, and let's make 2 lines by acute illness. There we go. Oh, now you can see why it's called we have a significant interaction, because there's differences in the shape, and they usually cross each other. When the lines cross each other, they have completely different shapes. That's usually evidence that you're going to see a significant interaction. And yep, we see that significant interaction, right? The income times acute illness. Well, what are we actually seeing? Well, now when you have an acute illness and you have low income, you have more depression than if you're already not sick. So in that could be then what was helping to explain why we didn't necessarily see earlier a clean difference between the 9,000 and the 28,000, because there was a lot of variability in that 9,000, particularly maybe in the amount of self-reported acute illness that people have. And then when we look more closely at now we still don't have, we didn't find a main effect for acute illness. So there's no difference between the groups, whether you have acute illness or not. Your depression scores are not significantly different, but your depression scores are significantly different when it's acute illness times your level of income. Particularly, we're seeing it in the 9,000 area, and I'll bet that's what the post hoc will show us. Yep. So the 9,000 no versus the 9,000 yes, that's where that significant difference is. Pretty cool, right? So that's how you would report it. And I don't think I necessarily need to type it all out for you. Again, you would just say a main effect. I apologize. I think I wrote employment status last time. I think I meant to say income. So I apologize. We have a main effect of income, right? And put in the appropriate 3,286, F 4.39, P less than 0.01, or if you want to just put P equals 0.005, which is less than 0.01, and a non-significant and main effect for acute illness, and a significant, or you could say, right, and a significant income times acute illness interaction effect, right? F3286 equals 3.31, P equals 0.02, put the eta squared. Results of the Tukey's HD found that individuals who earn less than individuals with acute illness who also earn less than $9,000 have significantly more depression than individuals who do not have a significant or an acute illness and they earn less than $9,000. We're also seeing that as before, in both groups, the more you earn, all right, once you get above a certain level, in this case, once you get above $28,000, you have significantly less depression than you have significantly less depression than earning less money, regardless of whether you have acute illness or not, right? So, because we're seeing that down here, the yes is significant, and so is the no. Actually, no, it's right. This one right here is telling us that if you do not have an acute illness, then as before, the 9,000 versus the 28 is not significantly different. But I would say overall, because we still have that main effect, right? Here we have that main effect. All right, so we did that. And let's do one more. What is the effect of chronic illness and health status on depression score? So now this is just be a 2x2 because the health status, if you look at our code book, what was health status? Yeah. Oh no, excuse me. This is another 2x4, right? Health is 4 levels. And then chronic is a 2. Is that what we're doing? Chronic. Yeah. So this is a 2x4. Chronic, yes or no, and health status, there's 4 levels. So let's do chronic, and let's do health status. Ah, we're getting an error. The design contains empty cells. What does that mean, empty cells? Let's look at something for a second. Let's look at let's look at a frequency analysis, frequency tables of health and chronic illness. And we see here, this is what's going on. So people who have chronic illness are reporting data across all the levels of their health status. And people who reported no on chronic illness are not reporting any data for the poor. So we have what's called an unbalanced design. We're missing elements in this 2x4. And that's why the ANOVA is giving us this error. But it says that there might be a way to fix it. Please try a different type of sum of squares. Well, where would that be? That's under model. So the default model is type 3, which is very good. We're not going to get into the granular details. You can look up what the different models are. But a type 2 model now controls for an unbalanced design, and then we end up getting our results. And here, what do we get? We have just a main effect for health. And in fact, right, if we plot that out, we should be able to see that let's put health on the x-axis and let's put chronic illness as the lines. And yet, right, see, no difference in the shape of the lines. They overlap, but we can also see where we have the missing values. We have no people who did not report chronic illness, who also reported that their quality of health was poor, which makes sense. If you don't have chronic illness, your quality of health is probably better than poor. And you would report all this the same way. You might want to say that you use the type 2 sum of squares, although we usually don't. Actually, when we do the narration, we're also, when we're giving papers, we're going to give the whole table, which is why I've had you practice exporting the entire results. Okay, so I think I share that granular, exactly. When running in ANOVA, especially more complex designs like the two-way ANOVA, the presence of empty cells or missing data can complicate the analysis. Type 2 sum of squares is particularly useful in these cases because of how it handles the interpretation of effects in the presence of unbalanced designs, when there are unequal numbers of observations across the levels of your factors, including some empty cells. Right, so that's it for the analysis. You have enough to do your assignments for this week. Now, there's a lot that we didn't go over, and that's okay. There's a lot you can learn from this. Some things that we didn't go over that you might want to play around with and you can learn through the JASP website are actually creating visualizations to see your assumptions check. One that is used a lot is a QQ plot, where you're actually seeing the visualization of the data along a theoretical normal distribution. So we might have some violations here, but I tend to not transform any of my data unless it's completely wildly skewed. And we might look at that more when we do regression. And then we didn't look at contrasts. And one of the most common is something called the polynomial, which is going to test the shape of your data. So if you have a very clear line, that's a linear contrast. If you have a nonlinear or an inverted U or a U shape, they call that a quadratic. I'm not asking you to do any of that. And I think you're good to go then for this week. So thanks very much, and I'll see you next week.